Hi and welcome to this video. My name is Jan-Hendrik and in this video I would like to show how to do calculus and logical expressions in R.
Hello, I'm Dr. Sheldon Cooper. Welcome to Sheldon Cooper Presents Fun with Flag.
For this video I planned the following. I would like to show how to do calculus with numbers and how to do calculus and logical expressions with strings. On top of that, we're going to do this with variables, with vectors, matrices, and, what is most important in this video, inside data frames. So with the vectors, the data frame is made of. I just switch to RStudio and show you how that works out. Here I have arrived in RStudio, and the first thing I always do is to open up a new script window. I give my code a beautiful headline, 5 hashtags, calculus and logical expressions in R. And the first thing we should do is to do that with numbers and strings. Okay, so calculus, calculating with numbers. Now we use R as a simple pocket calculator.
The pocket calculator was a small-sized electronic device used to perform the basic operations of arithmetic.
And give R a little task to add 18 plus 5. And I run this line, and in the command line we get the answer number 1. It is 23. So, since we all know that it is good programming style to use the print command so that everyone knows this shall be printed out on the screen, we use the print out command throughout this video. Well, that's adding, that's a sum of 18 and 5. Of course, we can do subtracting 18 minus 5, and we get the answer 13. Multiplication will be done with the star or the asterisk, 18 times 5, and that is 90. And we can do the division, 18 divided by 5, using a slash. Oh, why is there a space? By the way, it doesn't matter if there's a space or not. You can do it like this. You can run it. You can leave away all spaces. It doesn't matter at all. I just show you. It's exactly the same idea, but to be consistent, of course. I like to use those spaces. Well, this is basic calculus. Of course, we can also calculate in the power of. So, print 18 in the power with this little hat, 18 in the power of 5, and run this line, and we get the answer. The same can be achieved by 18 and 2 times the multiplication sign, 18 in the power of 5, and this will also lead to the same result. We have integer division. Integer division means just dividing what is dividable. So we use the percent, the division sign, and the percent, and divide by 5. I just run this line. It is 3. Why is it 3 again? Because integer division is what we learned at elementary school. At elementary school we learned that the 5 fits into the 18 exactly 3 times. But there is a rest. The rest is called modulo in mathematical expressions, and we can also get the rest if we like to print 18. And now we just use those 2 percentage signs, 18 modulo 5, And that will give the rest, which is also 3, but this is not the same 3 as before, because 3 times 5 is 15, and there is a rest of 3, and this is the multiplication rest. I can just show you how it is with 19. 19 divided by 5 is still 3, because 5 fits into 19 exactly 3 times, but the rest now is 4, because there is a rest of 4. Then, what comes first? Multiplication or addition? Of course, R can do this perfectly. I just give an example. 100 times 8, that's 800, plus 3 divided by 2, which is 1.5. So I expect the result to be 801.5, and this is exactly what can be seen here. Of course, I can reuse this code and use brackets, and they will be fully reflected. So if I put brackets in here to give the addition some priority, that will be correctly done too. Well, let's switch to logical operations or logical expressions.
Illogical. Damn it, Spock, you're right.
A logical expression or a logical operation always has the answer true or false. So mainly it's a comparison between two values. I just can show you what I mean. 18, is it the same as 5? So we compare 18 and 5, and the question here is, does 18 equal 5? Of course, it does not equal, and of course, I expect an answer false. Here, I just run this line and get this answer. Of course, again, it is better style to have the print around this expression. Nevertheless, the answer is the same. Let's make the check. So let's make the check if 18 equals 18. And indeed, true is the answer here, because 18 equals 18. Maybe you ask yourself why I said that this can be done with strings too, because I can compare two strings. Does Jan equal Eve? And of course the answer here is false, while if I compare Jan with Jan, the answer is true. We can now check if this is case sensitive. I just give Jan with a small letter J, and the answer is false. Accordingly, this comparison is case sensitive. We can also check for non-equivalence. So print 18 is not equivalent to 5. If it is not equivalent, the answer must be true now. And the answer is indeed true. Let's make the counter check again. So I used the same, but is 18 not equivalent with 18? And the answer here is false, because it is equivalent.
Hi there, it's Ernie, and today I'm going to talk about big and small, but
I can also check if 18 is larger than 5. The answer, of course, is false. I can check if 18 is small. I'm sorry, that was wrong. 18 is smaller than 5. The answer is false. Now I check if it is larger than 5. And the answer is true. If we want to check if it is larger or equal, we just add the equivalent sign here. Nevertheless, it stays mainly the same. We can check if 18 is larger or equivalent than 18, and this is of course true too. Well, what else do we have to do? We can make several logical expressions, so we can combine them using and or expressions. So let me just show what I mean. I just leave away the print so that you see what I mean. Is 18 equivalent to 18? And is 5 larger or equivalent to 5? And if I combine two logical expressions with an and the two and signs here are and expressions, both sides have to be true. Well, since 18 equals 18 and 5 is larger or equivalent to 5, both sides are true, so the whole expression, the whole combination, will be true here, and we get the answer true. But let us make the counter check that only one side is true. So 5 is not larger than 5. It is equal but not larger than. If I run this line, the second part, the second bracket here, will be false, and accordingly, since they are combined with and, both have to be true. This is not the case here, and we get the answer false. If we just want to check one side, and only one side has to be true and not both sides, we can use the OR operator. I just copy this, and I use a vertical line here. So I get this vertical line using the alt graph and the smaller or larger than key, but this can be different depending on which keyboard layout you have. So please check where you find this special character here. So this is an OR expression, and it combines both conditions here. 18 equals 18, or 5 is larger or equal 5. Of course, if I run this line like it is, both expressions are true, and that's fine, so it is still true. Now I can change the right-hand side. This expression is now false. Nevertheless, the left side is still true. Accordingly, we get a true. And I now set both sides to unequal. So both sides are false now. And now, of course, the OR combination or OR expression will be false. Of course, these logical expressions do not make so much sense with numbers, maybe with strings. Nevertheless, if we later on go into vectors and data frames, this will be very important, especially since we can do filtering on data frames using those logical expressions, and it is better to know how it works out. I just want to point out one important thing here. True and false can also be understood numerical, and true is translated as 1 and false is translated as 0. I just show you that this is really true. So if I just give print and true, of course the computer will give back true. But if I multiply true by 1, that doesn't make any sense, but it makes sense if we know that the computer understands true to be 1. And if the computer understands true to be 1, true times 1 is, of course, 1. Let's make the counter check. False. If the computer understands false to be 0, false times 1 should be 0, and exactly this is the case. Why is this important? This is extremely important later on when we build statistical models and we use dummy codification or dummy codes. If we use dummy codes, we can go with those logical operators directly into regression models because they are already dummy coded. The computer understands true and false to be 1 and 0, and those dummy codes can be understood by regression models. Of course, it is now crystal clear that the same is true with variables. So let's make it short and sweet. With variables. Of course, to show that it is true with variables, we need some variables. First of all, I just want to show that we just do calculus. And my variable a should be 18, and my variable b should be 5. I just run these two lines. And now we see on the right hand side in our environment that we have just assigned two variables. Variable a, which is 18, and variable b, which stores 5. And now of course we can do all that what we have seen, print variable a plus variable b, and run this, and we get the same answer than before. 18 plus 5 is 23. Logical expressions can also be done here. Logical expressions, so I can compare, or I just use the print command, I can compare variable a, where is it? There it is, and I check it for equivalence with variable b, and the answer is false, since 18 and 5 are not the same numbers. Now we can do the same with vectors.
I'm applying for a new villain loan. Go by the name of Vector.
Of course, I just fold away all the code that we have prepared so far so that we get a better overview. And of course, we have to assign several vectors first. So we need a vector a, and that vector a should be combined with c. That's always important. 1, 2, 3, 4, and 5. I run this line, and vector b should be assigned with 5, 4, 3, 2, and 1. And I run this line. And on the right hand side, in our environment, we see that the vector a has 5 numeric values, 1, 2, 3, 4, 5, and the vector b has also 5 numeric values, 5, 4, 3, 2, and 1. Well, basic calculus is pretty simple. Basic calculus is pretty simple. We can now add both vectors, vector a plus vector b. And if we do this addition, both vectors will be added element-wise. Element-wise, so 1 plus 5, of course, is 6. Can I mark this? 2 plus 4 is 6, 3 plus 3 is 6, and so on and so forth. So the answer will be 6, 6, 6, 6, and 6. We got an element-wise addition. The same, of course, is true if we subtract vector b from vector a. It is an underscore, of course. I run this, and we get the answer of element-wise subtraction. Let's copy that and make an element-wise multiplication, and let's make an element-wise division. Well, fine. So that's quite interesting. The same, by the way, is having the power, so exponential calculations, and so on and so forth. That all will be done element-wise. What else can we do? We can multiply a whole vector with a scalar or a single number. If we do this, It will also be an element-wise multiplication, but each element will be multiplied by 5. So that's not bad if we want to make several calculations based on that. If we want to rescale, for example, from Celsius to Fahrenheit, from centimeter to inch, we can make all those calculations even on a vector, so on a large data set, especially inside data frames later on. What is quite nice with vectors is that we have statistical functions on that. So, for example, we can sum a whole vector, so adding up all elements inside the vector, and that will lead to 15 because 1 plus 2 plus 3 plus 4 plus 5 is 15 here. We can do the same multiplicative, so 1 times 2 times 4 times 3 times 5. I run this line, and of course there's a typo. It must be the product of all, and that's 120 here. That's not so interesting so far. Now let's come to the more interesting functions like the mean. The arithmetic mean is meant here, and the arithmetic mean of 1, 2, 3, 4, and 5, of course, is 3. We can counter-check this by summing it up and dividing by the length of that vector. The length of that vector, of course, I just copy it and show it. The length of this vector is, of course, the length of that vector, of course, is 5, since it has 5 elements. And if I now run this line, the sum of that vector will be divided by 5. Again, come on. Really? There it is 3, which is, of course, the arithmetic mean. Well, if we can calculate the mean, of course we can also calculate the median. And the median is 3 here too. This is not necessarily the case if we don't have those symmetric distributions. Mean and median can deviate significantly, but here this is not the case. Well, what else do we have? We have the variance that we could calculate. Here's the variance, it is 2.5, and of course the standard deviation using the SD command. And there's the standard deviation. You all know that this is typically the square, not only typically, that this is the square root of the variance. Well, then of course we have a maximum operator. And of course we have a minimum operator. Both give 5 and 1, since 5 is the largest element and 1 is the smallest. Now we come to logical expressions, and that's quite nice because I'll just give it a headline. That's quite nice because we can do that element-wise. So let's take a look. I just compare vector A and check if it is equivalent to vector B. And that will be done element-wise. The answer here is false, false, true, false, false. Why is this the case? Because 5 does not equal 1, 4 does not equal 2, but 3 equals 3. So the third element of this vector is the same. The first 2 and the last 2 are not the same. I can also do a very interesting thing here. Vector A is larger or equal to the mean of vector A. Of course, this will also be done element-wise. and I get the answer false, false, true, 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 because the computer now checks on an element basis if each individual item, if each individual element is larger than the average element. So 3 is still equal or larger than the mean. 4 and 5 are, 1 and 2 are not, they are smaller than the mean. So I can make beautiful coding with these vector functions here. Well, some of you still know from school that there is more to do with vectors and more to do with matrices. And let me show you how that works out. In practice, you will, well, next to never use this. Nevertheless, the whole statistical models are all based on matrix calculations. So if you want to define on your own several calculations, statistical calculations, you can apply this set of functions here to make your calculations based on vector and matrix algebra. So let's go to matrices. And I just fold away the old code here. And of course we now need a matrix. And since I'm a bit lazy, I just use this command 1 to 25. So the colon is always understood to be as 2. So 1 to 25, running this will give a vector with the elements 1, 2, 3, 4, 5 up to 25. So if I use this, I can define a matrix A that shall be assigned as a matrix with the elements 1 to 25 by row is true, and the number of rows should be 5. Let's run this, and there is the matrix. It's an integer matrix 1 to 5, 1 to 5, so a 5 times 5 matrix. Let's print it. Let's have a look at it. And there's our beautiful matrix A, which comprises 1, 2, 3, 4, 5, second line 6, 7, 8, 9, 10, and so on and so forth. We need a second matrix, same size. That will be our matrix B. And our matrix B, maybe other elements, 11 to 35. I run this line, and let's take a look at that matrix. Should be a bit different. And there it is, 11, 12, 13, 14, 15, and so on and so forth. Well, of course, we can do the same with the matrices as we did with vectors. We can multiply a matrix, for example, matrix A times 10. That will be performed element-wise, so here we have 10 times that matrix. We can multiply matrices element-wise. Here is the matrix that is made of element-wise multiplication of these two matrices. But, oh, there is a gap. What's wrong? Here it is. Okay. And what else can we do with these matrices? Of course, we can perform a matrix multiplication. That will be done by matrix A, the percentage sign, the multiplication sign, the percentage sign, and matrix B. And now we will have a matrix multiplication. I just run this, and here we see the matrix product of these two matrices. Well, of course we can do several other things. We can make a diagonal matrix, for example, and that will be again print, and we use diag for that. A diagonal matrix, it shall have the 1, so it should be a 1 matrix. N row is 5, and n col is also 5. Let's print this, and here's our beautiful diagonal 1 matrix that comprises ones on the main diagonal here. Of course, we can transpose those matrices. I just make the diagonal matrix our matrix D, so I assign matrix D and I assign the diagonal matrix to this. And now I can transpose this matrix using the T command. No, I apply this to matrix D.
Are you stupid or something?
And here, of course, that doesn't make any sense. Let's apply this to matrix A. And there's our transposed matrix A. Well, and we can calculate the cross product. We use the cross prod. We use the cross prod command here. We apply this to matrix A and run it. So here's the cross product. We just check if this is really the cross product. We can use the transposed matrix A, and we make a matrix multiplication with matrix A again, and of course we put this into the print command because that's really stylistical better, and there's the cross product calculated manually. Last but not least, but I guess most important for you, is making these calculations inside a data frame. So let's give it a headline 1, 2, 3, 4, 5 with data frames 1, 2, 3, 4, 5. Of course, we need some data for that. I'm not going to make it much complicated. Let's make a vector length. So the body length of several persons. I assign it a vector with C, and we have one person being 160, one person being 170. Of course, I need dots and not commas, sorry for that. I need one person being 180, 190. Well, that's it, that's enough. I run this vector, and of course now I have the vector length with those body lengths with 4 elements. And I need a vector weight, and I store several weights in here. So let the very small person be 60 kilograms, then 65, then 86, and then 90 kilo. And now we put all that into a data frame. Let's call it data.frame, and we put the vector weight in, and we put the vector length in, and I just call those weight and length. Let's run this, and here's our data frame data, which now has a vector weight with the weights. Do we only have, yes, 4, and a vector length, and we can have a look at this data frame. There it is, a beautiful weight and length. Now, of course, as we all know, we can access the individual vectors and make calculations on that. For example, I can calculate the mean of the weights. So I use the function mean and I access the weight inside the data frame df data by $, and I use the weight attribute here and run it, and we see that our average person has a weight of 75.25 kilograms. Well, can we do more advanced things? Of course we can, because we can write back data into the data frame. I just want to show you with the example of the body mass index how that works out. So, body mass index. And maybe you know the body mass index is defined as the weight of a person divided by the squared body length. So df data $weight divided by df data $length squared. And we get back a vector with individual elements with an individual body mass index, 23.4, 22.4, 26.5 and 24.9. And now we can write back this vector into the data frame, df data, and I just invent a new name, BMI. And I assign this data into this data frame and run it. And now we see on the right hand side, df data now comprises for observation in 3 variables. I just double click it and there it is, weight, length and the individual body mass index. So in my daily work, I quite often use this, for example, for research in accounting. I have all the balance sheet data in the columns, in the vectors, and I calculate some KPI ratios or some financial ratios based on them, and I write them back into the data frame so that I add additional columns to the data frame. And that was it for this video. I hope you enjoyed watching. Please subscribe my channel and see you in the next video.
Stay here. I'll be back.